So, welcome to my second lecture. So, I will start by continuing a little bit on what I said yesterday and show you a few simple bijective proofs of partition identities using Ferrer diagrams, including one of Euler's theorem that I've been asked for yesterday by two people, actually. And then we will see some still combinatorial but non-bijective proofs of partition identities. So let me start with those proofs with Ferrer diagrams. So you remember Ferrer diagrams. So you just put boxes to represent your partition. So yeah, I don't know. So that would be, so that's 5 plus 3 plus 1 plus 1, for example. And I think Ali quickly mentioned that, but I'm going to repeat also one of the things he said. So there is a first very simple bijection that you can find using Ferrer diagrams. You can, by doing the reflection along this main diagonal, you can do something called conjugate. So it's the partition that you obtain by doing this reflection. So the partition obtained from lambda by reflecting the Ferrer's diagram along the diagonal. So that's equivalent to exchanging, the rows and the columns. So for example, the conjugate of our partition here would be 4, then 2, 2, and 1, 1. Okay. And so by just having this simple fact, you can do an extremely simple bijection of the following partition identity. Well, I will put theorem, but it's probably the less deep partition identity I know. Nonetheless, theorem. So the number of partitions of n with largest part at most k is equal to the number of partitions of n with at most k parts. And the bijective proof of that is just it's just 3 words, so it's take the conjugate. Okay, so that's probably the very simplest bijection you can do by using Ferrer's diagrams. And so in that particular case, it's quite clear that it's a bijection because, of course, it's even an involution because if you apply it again, you find the same partition. So okay, so that's quite simple. So now let's look at still simple but slightly more complicated partition identities. So there is one that I like because I find the manipulation quite elegant. There is an identity that says that for all n, Yeah, I forgot to write for all n here, but I guess you guessed that. So for all n, the number of, okay, so self-conjugate partitions. So by self-conjugate, I mean the partitions who are their own conjugates. So this number of partitions is equal to the number of partitions into distinct odd parts. Okay, so we'll do an example right now. So can someone give me a partition into distinct odd parts?
751.
751. Okay, thank you very much. So, yeah, so 7 plus 5 plus 1. So we will draw the Ferrer's diagram of this partition. So 1, 2, oh, that's a big one. 1, 2, 3, 4, 5, 6, 7. Then we have 5. And we have 1. Okay. So this is the Ferrer diagram. There is a particular fact that is true about the odd numbers, is that you can, if you want, isolate the box in the middle, and there will be the same number of boxes on both sides, right? Because, yeah, even odd numbers can be written as 2k plus 1, and you can isolate the 1, and you have k there and k there. Very simple. So you do this for all those little parts. And, okay, so far we haven't done much. But now what we can do is that instead of looking at it row by rows like that, we can rearrange this a little bit. And we will actually dispose those rows in the shape of hooks. So let me do that on the example, it will be clearer. So 1, 2, 3, 1, 2, 3. So for example, for the first part, 7 here, we will write it like that. I didn't change anything, just the disposition of the boxes. And then below it, there was a 5. Yeah, so we can do the same. And so we do it along the diagonal. We always place the red boxes on the diagonal, and we place those boxes to the right and below. Okay, so here we place the number 5, and we end up with the last one. So it was the number 1, which was just a single box. Okay, and the partition we obtain, it has a property. So we place the red box on the diagonal, and we said that there was the same number of boxes on the left of the red box than there are on the right of the red box. So actually the number of boxes that we will put on the first row is the same as we put on the first column, and same for this partition, this part, if you can still call it a part, etc., etc. So actually, the partition you obtain is a self-conjugate partition. So this one would be 4 plus 4 plus 3 plus 2. And yeah, but what is important is that it's self-conjugate. And here we took distinct odd parts, because when we do our manipulation, we want the result to still be a partition. And if, for example, here we had 2 parts equal to 7, we would have had a problem, because here it would have gone too far, and that wouldn't look like a partition. So that's the interest of taking distinct odd parts. And yeah, and so you can also do the reverse bijection quite easily by just like unfolding the hooks in the same way. So I think this one is simple but elegant. At least I like it. And it will be useful to also give you a bijective proof of, another bijective proof of Euler's theorem, because I have been asked yesterday if there are some more graphical bijective proofs of Euler. So I will answer that today. So yeah, I will just remind what Euler's theorem was. So it was saying, I will split my board first, that for all n, the number of partitions into odd parts equals the number of partitions of n, into odd parts equals the number of partitions of n into distinct parts. Okay, so yesterday I gave you a generating function proof and a bijective proof, but which was not graphical, in which we were just merging numbers together if they repeat. But here you will see, I don't know, graphical bijective proof, and which is due to Sylvester. So I didn't tell you about that only because I find it elegant. That's true, but it's also because it's a bit useful in what we are going to do now. Because we are also considering partitions into odd parts. So we'll now take a partition into odd parts. But now the parts are allowed to repeat, right? It's not like here. So I don't know. I'm gonna take an example inspired from that that example. So I don't know. Let's take more or less the same, but the 5 repeats. Why not? But what I said before, that every odd number can be decomposed like that by isolating the central element, that's still true. So we're gonna do that again. So yeah, okay, maybe I'm gonna draw it again also. 1, 2, 3, 4, 5, 6, 7. Up. So then there will be 2 5s and 1 like that. So we said we do that. Up, up, up. Okay. Okay. So I think the most common version of this bijection is also given by arranging things according to hooks. But yesterday, Ali showed me a version which is equivalent, but which I find nicer. So I'm going to show you his version of it. So you take this and you just rearrange the parts so that the red dots will all be in the same vertical line. So 1, 2, 3, 4, 5, 6, 7. So this is the red. And then we'll have 2 like that. And we have still a 1. Okay. So you write them like that. So far we haven't changed anything. We have just shifted everything a little bit to the right. And now what we are going to do is that on this diagram we are going to read some new numbers that will all be distinct. So what are we going to do? For the first number, we will take this central line and the arm here on the right. We could take on the left because it's symmetric, as you can see, but yeah, that's just a choice. Okay, so that will give us the first part in our new partition. So it will be 1, 2, 3, 4, 5, 6, 7. Oh, 7 again, why not? Okay, so 7. Then we take the second largest part that we can construct by doing something like that. And this will be here by going on the left and taking the vertical line just to the left of the red one. So we take like that. Okay, so that would give us a 5, I think, unless I'm mistaken. And yeah, of course, if I make a mistake, you stop me. Or if you have a question, you also stop me. Okay, and we continue this process. You take the largest hooks that you can get in this partition. So here it will be here, and it will be a 3. And here, you continue again. You still have some, well, you don't really see the hook anymore because it doesn't have an arm, but yeah. So you get a 2. And the very last one, very tiny here, it's a 1. Okay, so what we get is actually a partition into distinct parts. And we are sure it will be distinct because, so I'm not going to do every step, but just for the first one. So here you take this row, this column, which is the largest, and the arm. And here, it could have been that the vertical line would be as big, but here you just have the remaining portion of the arm. You don't have the red dot included anymore. So you're sure that this one will be strictly smaller than the first one we took. Etc., etc. You have the same process for the next ones. Okay, so this is the Sylvester bijection for Euler's identity. And yeah, and you can also do the reverse bijection by just putting things in shapes of hooks and like going back. But I still have many things to talk about, so I'm not going to be too, like, maybe too thorough on that reverse bijection. Okay, so these are the few graphical proofs that I wanted to show you, just to let you know that the Fair diagrams are also useful to prove partition identities. And I will quickly check the time and come back to that, to that board. Okay, perfect. Yes. So now I will mention possibly the most important and at least the most famous partition identity, which is well, actually there are two. It's the Rogers-Ramanujan identities. And actually Khan will show a proof in his lecture, he promised. So I will not give you a proof here. I will just state the identities, give you a bit of history, and then move on to some other identities. But this one is still very important. Okay, so yeah, so I will write Rogers-Ramanujan. Okay, so initially, those were not really partition identities, but Q-series identities, a bit in the shape of what you saw in other lectures yesterday. So they are the following. What am I doing? Up. Okay, so this is the first Rogers-Ramanujan identity, and there is a second one very, very similar to it. On the left, the only difference is that you have a plus n here, and on the bottom you have still QQn, and on the right it will still be some congruence class modulo 5, but instead of 1 and 4, it's 2 and 3 here. Okay, so both are quite similar. So the history of these identities is quite interesting to me because actually they were initially found by Rogers in 1894, and somehow at the time they went a bit unnoticed, and yeah, they weren't too famous. And then Ramanujan, who was working a lot about Q-series and partitions, but who, as you know, didn't always have proofs of what he was claiming, actually rediscovered them independently, but he didn't have a proof. And I think that was in 1913, if I'm correct. And then for a few years, he didn't really know how to prove them, even though he was sure they were true. And then in the library at Cambridge, he found at some point the paper of Rogers, where he proved those identities, and he was very much amazed by this work. And they even wrote a paper together with a simpler proof, or at least different, a few years later. I think it was in 1919. And somehow that was really in the air of the time, because Schur, also a German mathematician, also independently discovered it and proved it in 1917, I think. So yeah, many many people apparently were drawn to that to those identities. Okay, so these identities, so far they are in the shape of Q series, but if you followed correctly what I said yesterday, at least, and what was said in many other lectures, at least on the right, you must recognize something, I'm pretty sure. So, can one of the people who were not too familiar with generating functions before tell me for what this is the generating function? I don't know, some student maybe? No? Well, anyone else wants to save me from this lonely moment? Go ahead.
Partitions into parts such that parts are congruent to 1 or 4.
Yes, thank you very much. So indeed, so on the right you have the generating function for partitions into parts congruent to 1 or 4 modulo 5. And here, following exactly the same pattern, you have partitions into parts congruent to 2 or 3 modulo 5. Okay, so that's at least one side that's relatively easy to explain. And the other one may be a bit harder, but we have seen similar things in other lectures already. So I'm starting to draw, but maybe I should ask before. So n squared. Of course, that can be written in many different ways. But one possibility is to write n squared as 1 plus 3 plus 5, etc., up to 2n minus 1. So that's a partition, if you want, of n squared into parts where there is a difference exactly 2 between two consecutive parts. And if you want to do that graphically, you can, I don't know if I don't know, it's okay. I will do a small drawing just with 3 parts because I was a bit ambitious on the space, so it's okay. So very simple example, n equals 3. Up. So you can represent this as a staircase like that. And 1 over qq sub n, you saw that in other lectures, that's the generating function for partitions into at most n parts. So you can take this staircase and add to it some other partition. So, okay, maybe I also write that. 1 over qqn, generating function for partitions into at most n parts. Okay, so here we will take some, I don't know, some small example because I don't have enough space again. So let's just say we had, I don't know, something like 2, 2, 1 maybe. So you can just glue this to the staircase. So yeah, you attach this here, and this here, and you would get, I don't know, 7 plus 5 plus 2 here in that example. Okay. And more generally, you can also use one of the rules I said yesterday about generating functions, that if you have a pair of objects and you want to compute their generating functions, it's the product of the generating functions. So you can consider such partitions as a pair of a staircase on one side and a normal partition with at most n parts on the other side. And the generating function is the product. And then we sum over all possible sizes for the staircase. And in the end, you see that this is the generating function for partitions where parts differ by at least 2. Because here you start with exactly 2, and you add parts which are in non-increasing order. So maybe you will have some gaps which are bigger than 2, like here, or you will have some gaps which are equal to 2 if there were 2 consecutive parts that are equal, but you will have always at least 2. Okay, so I will write the partition version of the theorem on that blackboard. Oops. Okay, so Rogers Ramanujan. Partition version. Okay, and maybe I will just add numbers here. So that's the first one, that's the second one, and I will do the same here. So for all n, so the number of partitions of n. Actually, I will write maybe like the full thing, such that lambda I minus lambda I plus 1 is at least 2, so difference at least 2 between two consecutive parts, is equal to the number of partitions of n with parts congruent to 1/4 modulo phi. Or like plus or minus 1 mod 5. Okay, and because I'm slightly lazy to write everything again, I will do with another color the second one. So yeah, maybe I'll go quickly back to this blackboard, and it's really the same principle, except you can add. So here you have a difference of n between those two generating functions. So here you can just put one more column here. So that would be n boxes. So instead of considering the staircase 1 plus 3 plus 5, etc., you start at 2, you do 2 plus 4 plus 6, etc., which this time sums to n squared plus n. And again, you take a partition into at most n parts and you add them to the partition in exactly the same process. And in this way, you can see that the second Rogers-Ramanujan identity, it's still partitions with difference at least 2, but now you also have the fact that the last part, which I call lambda s, is at least 2. And so that's the only change on the left-hand side, and on the right-hand side, it will be plus or minus 2 mod 5. Okay. Yeah. So actually, this identity is quite difficult to prove compared to some other ones. It usually requires more than one lecture, and Can will do it. Yeah, even like finding a simple bijection is still open. There are some very, very complicated one of like 50 pages. But yeah, the simple is still open. And if some of you students want to look for that and find an answer, then you're instantly famous. So if you like fame and math, you can try that. And more generally, these identities were very influential in many fields of mathematics, and also just in the field of partition identities, because there were many other identities that have a more or less similar shape, by which I mean on one side congruence conditions and on the other side difference conditions. And therefore, all those identities are called Rogers-Ramanujan type identities. So I write that because in the next few lectures that I will give, we will study mostly or only, depending on what exactly I will do, Rogers-Ramanujan type identities. So type identities. So it's something in the shape, so for all n, so the number of partitions of n satisfying, so I will write it in the same order, so difference conditions equals the number of partitions of n satisfying some congruence conditions. Okay, and what I want to show you in this lecture, and maybe a bit in the next, depending on the time, is a way to prove some Rogers-Ramanujan type identities using first a combinatorial reasoning and then some equations, either recurrences or Q-difference equations. We will see that right now. And I will show you that on the example of Schur's theorem, which chronologically I think is the next important partition identity that was proved after Rogers and Ramanujan. And actually that's the same Schur who also proved Rogers-Ramanujan independently. So we'll do that now. Schur. So it was in 1926, this one. And so, yeah, I will write it into three different sets of partitions, but you will see that two of them are quite clearly the same, but I still do it. So let's, so of course, okay, let n be a positive integer. So let a of n be the number of partitions of n in two parts congruent to 1 or 5 mod 6. So that's the first set. Let b of n be the number of partitions of n, I'm lazy, into, oh, I can also use the into, so lucky. So into parts, distinct parts this time that I cannot reuse. So the distinct is important. Distinct parts congruent to 1 or 2 modulo 3 this time. And the last set, it's not a set, but the last number we consider C of n. So that's a number of partitions. Oh, I could have reused that as well, but okay. But I want, again, to give some names to my parts, such that, so for all I, you have lambda I minus lambda I plus 1, which is at least 3 in general, but if they are both multiples of 3, then there is some additional condition, and we can write it that way, that the difference between them must be at least 6 if lambda I and lambda I plus 1 are congruent to 0 mod 3. Okay. Yes?
Shouldn't we say that just lambda I plus 1 is congruent to 0 mod 3 and write 4 there because this misses some cases?
Why does it miss anything? Everything is included in the 3 already.
Because, sorry, yes.
Like it's 3 in general, and in particular it's even 6 if, yeah. But there are many different ways to write this identity. Some people write it, yeah, like indeed you can put you can say it's at least 4 if the first one is divisible by 3, or that works also with the second one. There are many choices, but yeah, here I don't know, I chose this one. Or sometimes you also just say the difference is at least 3 and you don't have consecutive multiples of 3. All of them are equivalent. I just picked one. Okay, so I will first show you why it's relatively easy to see that A of n and B of n are equal. Well, no, I don't need to erase, I can just move. Okay, so I'm not gonna need that right now. Okay. So, yeah, proof that A of n equals B of n. So that will probably ring a bell from what I did yesterday with Euler's theorem. So this is with, we will prove that with generating functions. So let's start, I will start with B because I prefer it in that direction. So the generating function for partitions into distinct parts congruent to 1 or 2 mod 3, I will write it as a product again, not with Kupo-Schammer symbols, because I will do some simplifications and I prefer it that way when I do that. So it's the product of 1 plus 3k plus 1, 1 plus 3k plus 2, 4k non-negative. And the generating function for A of n, you also know it from a lot of things we have said, so that's 1 over q, q5, q6. So let me just do my usual trick that I did yesterday on that. And I can, again, multiply and divide by the same things. I can do something like that. 3k plus 2, and you divide by the same. Okay, so just like we did yesterday for Euler's theorem, these two things together, it will be 1 minus q 6k plus 2, and these two things together will be 1 minus q 6k plus 4. So we end up with 1 minus q 6k plus 2, 1 minus q 6k plus 4. And in the denominator, so here you have the product of 1 minus q to the n for all n congruent to 1 or 2 modulo 3. But if you want, you can also rewrite this modulo 6. It's just another way to write it, but it's still the same thing. So we can say that 3k plus 1, it's either of the shape 6k plus 1 or 6k plus 4. And this one is the same. It's either 1 minus q 6k plus 2 or 1 minus q 6k plus 5. And then you will have some cancellations, just like we had yesterday. So this term will cancel with this one, and this term with this one. And we are left with 1 over q6 and 1 over q5 q6. So that's the generating function for partitions into parts congruent to 1 or 5 modulo 6. So the first, so the partitions counted by A of n. Okay, so that's this first equality. So now we know that these two are equal, and that wasn't so hard. So usually what is actually called Schur's theorem is either like B equals n or B of n equals C of n or A of n equals C of n, because that's the more challenging part, and that's what we will do now, I think. I always check now, I still have some time. So we will start the proof, which is good because the equations will be a bit long, so I will do the equations tomorrow, but I will do the beginning of the combinatorial reasoning now. Okay, so even from this proof and from what we said until now, I think you agree with me that the generating function for A of n, or equivalently B of n, is much easier to compute than the generating function for C of n. Or maybe you haven't tried yet, but if you try, you will see it's a bit less immediate. Okay, so now we want to prove that C of n equals B of n. You could also prove A of n, but like with my technique, it's simpler to prove B of n. And so what we will do is that we will start from the generating function for C of n and show that it's the generating function for B of n that we know very well. Okay, so idea. So start with the generating function for C of n and show that it equals minus q squared q3 infinity. Okay, so I promised a combinatorial proof, so you will have it right now. So I will introduce a few more notation before doing that. So let's start, definition maybe. So instead of just computing the generating function for C of n, we will add one more parameter, which will count the largest part of your partition. So I will call G sub m of n. Yeah, I'm taking G, but there is a there is a reason that I'm not taking C. So that will be sorry, that's not of n, that's of q. So that's be the generating function for partitions for partitions counted by by C, such that the largest part is at most m. And maybe here it's not fully necessary, but in some more complicated proofs I will do later, I also like to have another generating function, which I will call E of m, which will be almost the same thing, except the largest part is exactly m. Okay, so first there is a very simple relation between the G's and the E's. So I claim that EM is equal to GM minus GM minus 1 of Q. So that would be true for any, like if you take any type of partition and you add a restriction on the largest part, then that would always be true. Because here you take the set of partitions where the largest part is at most m, and here you remove all those where the largest part is at most m minus 1, so there only remains the m. Okay, and now what we want to do is compute some of those EMs, which then we can express in terms of the GMs. And that's what I'm going to do now. I will erase my first blackboard, which was this one. So if you look at Schur's theorem a bit carefully, you see that those difference conditions, they depend on the values of the parts modulo 3. So it's a bit of a heuristic rule, but it's, as far as I know, at least in all the examples I studied, it's always true. Then when you consider your generating functions, it's good to distinguish all possible cases modulo 3 for the value of our m here in the subscript. Sorry. Okay, so we'll look. So we want to compute. Well, not really compute, but we want to find equations for, let's say, E3m, E3m plus 1, and E3m plus 2. Okay, so all possible values modulo m. Okay, so we'll do that. So let's start by thinking. Maybe I will start with those two because they don't have any particular conditions, so maybe it's simpler. So let us consider a partition. So generated by E3m plus 1. So by the way, I stopped writing the Q's between the parentheses because they are always the same, so I sometimes just don't write them. I hope you're okay with that. Okay, so such a partition is of the shape. So it starts with 3m plus 1, right, by definition, because we take partitions whose largest part is 3m plus 1. And then you have some second part, lambda 2, etc., and some last part, lambda s. And all these parts, they satisfy the difference conditions from Schur's theorem. So in particular, if you only consider those, they also satisfy the difference conditions, right? It's even a less strong statement to just say that. So if you single out this first part and you look at the rest, this is, it's a partition satisfying the difference conditions. Maybe I give a name to those difference conditions. I don't know, I will put some star. So they satisfy the difference condition star. And we should just look at the difference conditions to know if there is a restriction on lambda 2. And of course, there is, because between 3m plus 1 and lambda 2, there needs to be a difference at least 3. So we are looking at this case because 3m plus 1 is not a multiple of 3, so we don't need that second condition, it's just a difference at least 3. And yeah, then you can have any other possibilities, but you have the condition that lambda 2, and lambda 2 is at most 3m minus 2, which is this one minus 3. Okay, so, and this is exactly the conditions that are satisfied by this partition. And in terms of generating functions, again, you can see this as a pair where the first element is this one and the second element is this partition. So that would mean that E3m plus 1, well, I will write off Q again because there are Q's in the formula. So it's the product of the generating function for this part, which is simply Q to the 3m plus 1, and the generating function for this partition, which is G of 3m minus 2 of Q. Okay, so that's a recurrence equation, if you want, or at least a relation between some E and some G. And for later purposes, it's good to have only G's. But for that purpose, it was nicer to really see that the first part is fixed. So I will use the proposition there to just rewrite things a little bit. And we will get that G 3m plus 1 of Q is equal to G 3m of Q plus Q to the 3m plus 1 times G 3m minus 2 of Q. Okay, so that's, I hope I did not make any mistake, but I think so far, so good. So that will be our first equation. Is that clear for everyone, even those who hadn't seen that before? Yeah, okay. Okay. So, yeah, I will do, actually, the case for 3m plus 2 works really exactly in the same way, so maybe I go fast or almost don't do it. You have something like 3m plus 2, plus again some other partition, and so that satisfies the difference condition star, and also you have that lambda 2 is at most, using the first condition again, because this is not divisible by 3, you just have that this is at most 3m minus 1. And by doing exactly the same thing, you can get a second equation, which I'm skipping all the steps, I write directly in this shape. We have that G 3m plus 2 of Q is equal to G 3m plus 1 of Q plus Q to the 3m plus 2 this time, because we extract this part. And here we have G 3m minus 1 of Q. So this is the second equation that will be important for us. And let's do the last case with slightly more detail. So now we consider a partition whose largest part is a multiple of 3. So we have something like 3m plus, again, some other partition. And, well, again, this partition will satisfy the difference conditions. But now you have to be a bit careful for the 2. So for the lambda 2, sorry. So 3m is divisible by 3. So if lambda 2 is not divisible by 3, that's okay. You can still have a difference at least 3. So if it's 1 modulo 3, you will have a difference at least 5. And if it's 2 modulo 3, you have a difference at least 4. But if it is actually divisible by 3, then you would have a difference at least 6. So here we come back to what Karen said before, because all this combined means that lambda 2 now has to be at least 4 smaller than 3m. So it's at most, I said at least, but I meant at most, sorry. It's at most 3m minus 4. Okay, so yeah, still, apart from the fact that you have to consider a bit more details, the global idea is still the same. And I will also directly write the formula with the g's. So you have 3m of q. So here you have 3m minus 1 of q plus q to the 3m, because again we remove the first part, and the only difference is here we will have 3m minus 4 of q. Okay, so here we have 3 recurrences that are only with g's. We got rid of the e's already. Yeah, in some other proofs they stay a bit longer when things are more complicated, but here they were quickly gone. And so what we will do tomorrow in the next lecture is that we will try to combine these 3 equations to obtain an equation where all the indices have the same value modulo 3. And why do we want to do that? It's because actually what we will try to find will be, so goal of tomorrow, it will be to find the limit when m goes to infinity of, well, it will be, I hope I'm not going to say anything wrong. I don't remember. I have a doubt whether it was 1 or it's 1. Yeah. Or if it's not 1, there is a small probability that it's 2. But I hope you don't mind. You'll see tomorrow. Let's put a bit of suspense. So we will try to find this limit, because then when m goes to infinity, the bound on the largest part also goes to infinity. So you will have all the partitions that satisfy those difference conditions with no restrictions on the largest part. And to do that, we will use our equations and some other tricks that you will see tomorrow. So see you again then. Thank you.